So today's topic will be talking about statistical power and ANOVA. I will say that this one does start with, it does say it's statistical power, but most of this study group will be looking at different kinds of statistical testing. A better demonstration of statistical power I'll actually be doing tomorrow, just because tomorrow's study group, I have a notebook already set up. It's on the repo. And that one, I will be going through setting up statistical power in a statistical experiment. And also we'll be going through an example of A/B testing. But really quickly today, what we'll be talking about, we'll be doing one more quick dive into statistical power. We'll be talking about Welchs Ttest, which is a different kind of t-test from what we've learned before. We're also at some point in this slide deck gonna summarize all of the statistical tests that we've seen so far, followed by the Kolmogorov-Smirnov test, which is another test that is kind of useful for us, as well as an ANOVA test. So I'm not sure why they called this section ANOVA, even though it's just one of the many tests covered in this section. Something that I did put on the homeroom that I just wanted you all to be aware of is that similar to how, last phase, there was one topic that I said, if it's, if you're working on other stuff or if you find yourself short on time, this is the topic that I would suggest you can skip. Just because a lot of these tests are more auxiliary, and plus the Welchs Ttest, which is the slightly more important one, we'll be going through an example tomorrow, and it is also the t-test being used in, I think, 2 of the A/B testing examples in our lessons. All right, so let's start with statistical power. I think end of last week we had talked about statistical power being defined as 1 minus beta, and beta is the probability of a type 2 error, which is a false negative. And so it is also defined as the probability of rejecting the null hypothesis when it is indeed false. So it is a true positive, rejecting the null hypothesis when it is false. And remember that the alternate hypothesis is usually the positive category. So if you have power equals to 1, which is sometimes possible, you basically have a perfect test that always correctly rejects the null hypothesis. So there we have it. Just to remember, I have it on this slide just so we know, the probability of a type 2 error is failing to reject the null hypothesis when it is indeed false. So an example that we'll look at tomorrow, after you select alpha, you can typically determine a threshold to maximize the power of a test, and that is the simulation that I'm going to walk through the code of tomorrow. All right, any questions about statistical power? Because I think we're actually going to move on to all our other tests after this slide. All right, and just so y'all know, the very first, the code that I'm going to go through tomorrow is from the very first lab of this topic. So it's the statistical power lab, and I'll be walking through that code tomorrow. All right, so the first test we're going to talk about today is the Welchs Ttest. So the Welchs Ttest differs from a 2-sample student's T. So last week we talked about 1 sample and 2 sample t-tests. Typically, if you just have t-test and they don't say like what t-test it is, the full name is a student's t-test. The guy who created it, his name was student, I think. So last week we were doing student's t-test, and today we're going to talk about the Welchs Ttest. And the only difference for the Welchs Ttest is that it takes into account different sample sizes and unequal variances between samples. So as you can see here, I have like kind of a mild table here where we have the t-statistic and the degrees of freedom for the 2 tests. I do think that if you were to have the same variance and same sample size in your Welchs T, it will be the same as your student's T. So just so you know. So Welch's T is a little bit more complicated just because it takes into account these different sample sizes and unequal variances. And one more thing that I think I forgot to mention is this is only for 2 sample t-tests. So Welch's T-test is a 2 sample t-test that takes into account different sample sizes and unequal variances. And these are the statistics. The one-line code that you would use for this, I think, is the exact same one as you would use for the t-test. And all you have to do is add in specific arguments that tell it the different sample sizes and unequal variances. Tomorrow, because we're going to be looking at an A/B testing example, and Welch's T-test is actually the one used more for A/B testing just because you can have different sample sizes. And the example we'll be looking at is, I think, a marketing website where you have one marketing campaign for, I think you have 2 different versions of a marketing campaign, and you look at the difference between the 2. And so for that, we'll be using a Welch's T-test.
So Ish, is it like the difference between the t-test we were doing before and this one? And the t-test we were doing before, we got like the standard deviation of both, and then we multiplied it by, whereas this one we're looking at like the individual standard deviations and dividing it by the individual ends. So that's how it takes into account.
Yeah, so this one is different. So here you can see that there's a, oh, sorry, you're still saying.
No, go ahead, keep going.
So the student's T, we have actually a separate formula for a pooled standard deviation, which actually does in some way take into account the sample size as well, but not in as much detail as it does for the Welch's T-test.
Okay, gotcha. So they have the individual standard deviations instead of the pooled one, basically.
That's right.
Okay.
Yeah. So I think because of that, because you want to be more sensitive to different sample sizes, Welch's T is actually used more commonly for A/B testing.
Gotcha.
Cool. Any other questions on the Welch's T-test? All right, and to conduct the Welch's T-test, very, very similar structure to what we were doing before. You set up your hypotheses, decide on your alpha, calculate your statistic, and interpret your p-value. I feel like we don't have to go through an example because you can use the same example from a 2 sample t-test. All right, now as a quick stop, I do want to quickly summarize all the tests we've seen so far. So we have 1 sample test, which is this first block of words, and then we have 2 samples tests. So I do also have a table summarizing all of these things for all of the tests, because we still have a couple more to talk about right after this slide. But just wanted to quickly summarize. Basically, we've seen 4 tests so far. We've seen 1 sample tests and 2 sample tests. So first of all, with our 1 sample tests, we're always asking, is 1 sample different from the population or not? Is it statistically significantly different from the population? And that's when you want to do a 1 sample test. And our example here is, does tutoring have an effect on the IQ of students? Or I think the other example we had was, does, I think it was sales training have an impact on the amount in sales that a person makes? So here we have the 1 sample Z test and the 1 sample T test, both of which we talked about last week. 1 sample Z test is when you know your population standard deviation, and a 1 sample T test is when you don't know your population standard deviation. So whenever you're faced with a 1 sample problem, you really are just looking out for, do I have my population standard deviation? Honestly, most of the time you don't, which is why p-tests are more common. But if you happen to have the standard deviation, you will use a z-test, and that is the distinction between when to use which one. Next, when you have 2 samples different from each other, those are your 2 sample tests. And examples are, I think last week we talked about drug effectiveness. I think we were talking about, was it systolic blood pressure? We're looking at the effectiveness of that, and also A/B testing, example of which we'll talk about tomorrow. And here the 2 tests that we've talked about are the regular 2 sample t-test or student's t-test. If the samples have same size and variance, of course you can still, if you notice the t-statistic values for that one, you can still feed it in different sample sizes and variances, just that the Welch's T-test takes better account of these differences. It's just a different way in which the statistics are formed. It's just the Welchs Ttest is more sensitive to different sample sizes and variances, which is why if you know you have different sample sizes, Welchs Ttest is usually preferred. Now, these are all the 4 tests that we've talked about so far. Does anyone have any questions about any of this? Awesome. So the rest of this slideshow, we're going to talk about 2 other tests that are quite different. The way that the hypotheses look are not similar to this, because here you're comparing, population to sample, sample to sample. We're going to see in the next couple of tests a little bit different. So the next test we're going to talk about is the Kolmogorov-Smirnov test, or the KS test. So all the tests we've seen so far actually have some sort of normality assumption. You're assuming that the underlying distribution of all of these tests that we talked about before come from some sort of like normal distribution or t distribution, which is similar to a normal distribution. And something that we can do to check if something is normally distributed is actually using the KS test. So the KS test checks for whether something is normally distributed. And so what I think is written here, the one sample KS test, which is the longer name for it is the KS goodness of fit test. It tests for the similarity between a sample and a normal distribution. And it actually does that in terms of the difference between their CDFs. And if you remember, CDFs is the cumulative distribution function. And so as an example, this is an example of 2 different CDFs. We have one of them, which comes from a normal distribution. And in this case, it's not as clear because it's usually randomly sampled. So in one of these CDFs, we have a normal distribution. And one of the other CDFs, we have the sample that we're testing. And what we do here is we're actually looking at the difference between their CDFs, and that's what we're using to test. So setting up a KS test. Oh, by the way, any questions before we move on from the setting up of a KS test?
One of them are the population and the other one is the sample?
So not exactly. Both of them are actually samples. We're just testing to see whether a sample is normally distributed. One of them is just a random sample that you have that you want to test, and the other is a sample drawn from a normal distribution. And we just want to see how similar their distributions are. So this test is used for, let's say you have a sample, and we're actually going to see for linear regression on Friday. You have to check that things are normally distributed, and you can do that with this KS test. Anything else? All right. So setting up the KS test, the hypotheses for a KS test is, the null hypothesis is that there is no difference between the distribution of a sample and a normal distribution, basically saying that the sample is normally distributed. The alternate hypothesis here is that there is a difference between the distribution of a sample and a normal distribution, so therefore the sample that you have is not normally distributed. So we can set our alpha at 0.05 as usual, and here we have the test statistic, which is D. The test statistic D, as I was showing here, is literally the maximum distance between your 2 CDFs. So what the KS test will do in Python, it will, in the backend, plot the 2 CDFs and just look for the point that there's the biggest deviation between the 2 CDFs. So you have 2 CDFs here, and we're really just looking for where is the biggest difference and what that difference is. So that difference is B. And that is actually our test statistic. So here you can see it's the max of the absolute value between the 2 CDFs. So with that test statistic, you can actually compare it to a critical D from the D table. So with this KS test, pretty simple. you can see here, we'll look up for alpha of 0.05, what your critical value of D is, also based on your sample size. So based on your sample size, so let's say, I don't know if I have sample here. So let's say we have a sample size of 10. Our critical D will be 0.4. So if our test statistic D has a greater difference, if the difference between CDFs is greater than 0.4 at any point, we can reject the null hypothesis and saying that there is a difference between the distributions and our sample is not normally distributed. You can either do that, or when you use SciPy, they actually give you the D statistic and the p-value straight away, so you don't have to look it up. And if the p-value is below 0.05, you can safely reject the null hypothesis. Questions on this part so far?
We have a sample size and we are comparing it to a normal distribution, right?
That's right.
And this normal distribution, what it is, how we can find it?
So the normal distribution, they will actually use the statistics from your sample. So for example, your sample, it might not be normally distributed, but let's say it has like a mean of 10 and a standard deviation of like 2. For that normal distribution, they will sample, they will take a sample from a normal distribution that has a mean of 10 and a standard deviation of 2. So you have the same statistics, but you can still have mean of 10 and standard deviation of 2 without coming from a normal distribution. So you might have, a mean of 10 and a standard deviation of 2, but having some sort of other weird distribution. And so what this test is doing is comparing the distribution of the two. I don't know if that makes sense. All right. So yeah, again, it's a one-liner in Python, and they output the p-value so you can immediately reject or fail to reject the null hypothesis based on that. So here we talked about a one-sample KS test. Something else that also exists is a two-sample KS test. Similar but slightly different. The two-sample KS test tests for whether two samples were drawn from the same population or two identical populations. So those two scenarios, same but different. So it's either you're drawing two samples from the same population or two separate populations that happen to have identical means and standard deviations. So hypotheses actually very, very similar to the last one. Null hypothesis is there no difference between the two distributions. Alternate hypothesis is that the two distributions are just different. And in a very similar way, you're just comparing the CDFs of both samples. And so you can see here, the test statistic D here, instead of it being from a normal distribution, and I believe this one is the one for a normal distribution, instead of that, you just have 1 and 2 because it's just two samples. And again, we can actually use the same diagram with two CDFs. We're just looking for where there is a maximum difference. And from there, there's actually a separate D table for two sample KS tests. So if you look at the two sample D table, it works slightly different. You're looking at the sample sizes for the two samples. So you can actually use this table to see the different sample sizes. Or if you have bigger sample sizes, there is actually a formula that you can just plug in to find out what your critical D are. This one less so used in my opinion. I do think that there are opportunities to use it in your EDA process, but not super necessary for this project, just so y'all know. But yeah, there's also a built-in function for this, so not to worry. So same thing, reject the null hypothesis if your calculated D is greater than your critical D. And so if you reject the null hypothesis, you're just saying that your two samples are from different distributions. Questions on this?
Yeah, I had a question. Since we're doing a cumulative function, wouldn't one extreme outlier immediately make the test fail? So any sample with that one outlier would just immediately fail it?
No, because it's cumulative.
I think, that's a good question. I think it's possible, yeah. If you have like an outlier big enough that it pulls your CDF, I could see that. Yeah, because it depends on your range of values as well. Yeah, I could see that happening. That if you have like one big outlier, you could lead that to immediately reject your null hypothesis.
Isn't the CDF though like an accumulation of all the probabilities, and then an outlier, it would be the probability of that outlier, right?
Yeah.
So wouldn't that not necessarily be, I don't know.
But because your X values are plotted along here, so imagine if, let's say, I guess here we have, I don't know what kind of, this is a logarithmic scale, but imagine we had like 0, 10, 20, actually, let me annotate it better. Let's see. So a CDF, you have your probabilities on the y-axis and then your actual values on the x-axis. So if you were to have like an extreme value, like let's say for the normal distribution, your extreme value like sort of ends there. But you have in like your sample distribution, you have like a value out here. So if you have value out here, it's sort of, I think, I see what you mean. I have to think about this more.
Wouldn't it just have like not as much of a probability, so it wouldn't impact the CDF? I don't know.
Yeah, I would say if you have like an outlier, what happens is that, I'm not too sure about the scaling of it because your X values would be different. But if you have outliers, your CDF will look more like, let's say, if you have an outlier on the very high end, it will flatten out. You know what I mean? But it'll flatten out a lot sooner. Or you'll have like a longer flat area if you have an outlier on the high end. Because you're right, because the X difference from here to the top is less. But yeah, I've never really thought too much into this, to be honest, but but an outlier will kind of shift or skew your CDF a little bit. But that's a good question. I do want to like look into it a little bit more, and if I find any good resources, I'll send them out into the channel again. So thanks for that. Any other thoughts or queries about the KS test, either one sample or two sample? Let me write that down.
So in a hypothetical situation, what happens if it does not pass the test? So it's not normal? Does that mean you can't use the data, or do we just have to find a way to manipulate it to make it normal? Yeah,
so for the one sample test, which is the one that we're testing if something is normal or not, we'll see that it does depend on the situation. For a linear regression, if like the distribution of residuals isn't normal, it does, and we'll talk about this on Friday, but if the distribution of this part of a linear regression model is not normally distributed, it actually makes your model a little bit less valid. It makes it a little bit less reliable. And because of that, usually the conclusion is that, all right, a linear model doesn't work for this data as well as it should. And therefore you would actually go and look into other models. And so that's like one of the main testing for normality things that we'll be doing for the rest of this phase. Just because linear models have these assumptions, which we'll see on Friday, or if anyone has looked into topic 18 already, linear models have all of these assumptions that are important that are fulfilled for the model to be reliable and I guess like trustworthy, or what's the word I'm looking for? I think reliable is the best word I can think of right now. But yeah, we'll be doing normality tests on our data for linear regression. And if it doesn't pass those tests, you would usually conclude that, all right, this model might not be valid, or I have to edit my data in such a way that it will satisfy these assumptions. And we'll talk about the ways we can go around doing that probably next week, early next week. Yeah, that's a good question as well. Anything else? I will say the KS test is also built into our, it's also built into Python, when we run a linear regression, there's like another one-liner that will plot all of your normality plots. If some of you saw presentations from yesterday, there's like this plot with like a red line and like blue dots around it. That is a test for normality. All right, if there's nothing else about the KS test, the last test we want to talk about for this entire phase is the ANOVA test. A lot of text over here, but ANOVA test is comparing group means with regards to a single variable. So it's looking to see if there's a statistically significant difference between groups. Before I get into this part, I just want to talk about an example. And you would basically use an ANOVA test for an example like this. Is there a difference between the mean GPAs of freshmen, sophomores, juniors, and seniors? This test statistic is F, which is really complicated, so we never have to talk about it because our one line of code, which I'll actually show you in the next slide, will give us the statistic straight away. But basically, we're comparing the difference between means of different groups. So very, very similar actually to a t-test. Some people might actually think about ANOVA tests like doing multiple t-tests. So here you would set up your hypotheses as null hypothesis being that there is no difference in the means, and alternate hypothesis being that there is a difference in the means. And your alpha 0.05, and test statistic being this F statistic, which you can then get a p-value from to interpret. Why the ANOVA test exists. As I mentioned, it is like a multiple t-test. So it's like doing many t-tests, but doing an ANOVA test instead of doing multiple t-tests gets rid of the multiple comparisons problem. I think that there is a reading in topic 15 about the multiple comparisons problem. It's a good one to read just so you know like where it comes from and why it exists. But basically, to summarize, if you think about, all right, a single t-test yields a p-value of 0.03. So that means that there's a 3% chance that your conclusion to reject the null hypothesis is spurious or by coincidence, and that's our definition of a p-value. I linked here this thing about spurious correlations that I will show later on. But if you have a p-value of 0.03, the probability that you correctly rejected the null hypothesis is 0.97, which is, you know, pretty good. However, if you were to do multiple t-tests, so let's say, you know, you had many, many groups of data and you wanted to compare if they're similar or different to each other. If you have this probability of 0.97 of correctly rejecting the null hypothesis, but if you do this 100 times, based on our probability, we know that the probability to do this 100 times, you're taking 0.97 to the power of 100, which brings your probability down to 0.04. So the probability of correctly rejecting the null hypothesis, like for example, 100 times, or basically any number of times increasing from 1, your probability is going to dip exponentially. So that's where the multiple comparisons problem comes from, which is why the ANOVA test was created, to just get rid of that, to take that into account. Yeah, any questions about that? I linked here spurious correlations. This is kind of funny. I'm pretty sure people have seen this before, but it's basically things that happen to be correlated that have no link at all. Like for example, you can see here, US spending on science, space, and technology happens to correlate with suicides with a correlation coefficient of like almost of about 99.8%. And this is a really funny one. Things that are correlated but have nothing to do with each other, which is the idea of spurious correlations, which is sort of, I mean, I like to think of this when I think about p-values. Just things so happen to be that way. But yeah, that's a fun one. And also I have here, if anyone is interested in looking more deeply into how the ANOVA test works and how it gets rid of the multiple comparisons problem. I think in terms of like the mechanics of why that is and how that works, honestly not very important for us in data science, because we only really use ANOVA to do EDA and just test out hypotheses that we might have about our data set. But yeah, there's that. So how do we do an ANOVA test? And this is sort of like a preview into linear regression. This is how an ANOVA test outputs in Python. So we're actually going to be talking about this syntax a lot more at the end of the week going into next week, because this is what we'll be doing for our project. I'm sure you've seen some, I don't know if anyone had this on their presentation yesterday, but this is what you'll be coding. Basically, OLS that we're importing here is ordinary least squares, which is the kind of linear regression that we're going to be doing. And to get this ANOVA output, it is an output of our OLS model. And basically you see here, this is an ANOVA output. Just for some context, the data that I'm using here is data about supplements and dosages and their effect on tooth growth. So this ANOVA test is comparing, is there a difference between amount of tooth growth? And this I think is measured in, I don't know, I want to say millimeters, based on these supplements. And here you can see that there are two different supplements. There is VC and OJ. And then within those supplements, you also have different dosages. So you have doses of 0.5, 1.0, 2.0 for VC, 0.5, 1.0, and 2.0 for OJ. And what this ANOVA test is doing is you're just looking, you know, across the different supplements and across the different doses, is there a difference in the means? So looking at this output over here, we can see p-values all lower than 0.05. If anyone, I'm pretty sure we've all seen this notation by now, but if you see an E followed by a number, it just stands for 10 to the power of that number. So here we're basically looking at 4.3 times 10 to the power of -4. So we're looking at 0.0004. And here, 17 digits. So these p-values, very, very small, so we can actually safely reject the null hypothesis, and all of these have significant differences between their groups. I think this is my last slide. So yeah, this didn't take the full study group, but any questions about this? All right, well, as mentioned, this topic
These
is
are
a
all
little—
just basically different forms of hypothesis testing.
Yes, exactly. These are all different statistical tests that you can choose to run on your data if you want. But I will say that for data science, running statistical tests is not something that we do very much, with the exception of A/B testing, which I'll talk about tomorrow. But yeah, there are so many different kinds of statistical tests that exist. The ones in the curriculum are just the more useful ones for us, but I will say, yeah, data scientists usually do not do statistical testing, but these are just good to know. When we talk about linear regression on Friday, we'll see that what linear regression is doing is actually doing a bunch of t-tests. But we won't be actually, you know, going through the statistical testing process of conducting a t-test. All of the t-test p-values and t-statistics will be already computed for you, and you just have to interpret them. So, so yeah, that's why we need to at least know a little bit about the testing process. But any other questions? I do want to talk about like the structure for the next week.
Just a quick question. It's a little off topic, but for Bayesian analysis, so that's kind of is that just a standalone topic that is not necessarily applicable to what we're working on with linear regression?
Yeah, so Bayesian analysis, or I think it's Bayesian statistics is the name of the topic. Let me actually pull up our phase real quick. So what am I doing? It's over here. So here in Bayesian statistics, it is kind of a standalone topic. For that study group, I will be going through one actually very, very common interview probability question that is a little bit of a level up from the ones that we did on on Monday, yesterday. But that one happens to be way more common interview question that we'll talk about. I'll talk about the Monty Hall problem. And also these two, MLE and MAP, are actually very, very big picture, the philosophy of modeling. So the math behind this is pretty in depth. Like I will say, I'm not even like very, very comfortable with the math that it goes into. But for us, it's a very big picture. What is modeling doing? Which sort of leads us into our first modeling project, which is for linear regression, and all of the modeling we'll be doing in the next couple of months, next couple of phases. So that's why this topic is here. It is quite a standalone topic. You typically wouldn't even go into maximum likelihood estimation or a priori estimation unless you get into advanced statistics. So this is more for like big picture things. I will be like drawing a bunch of diagrams to like try and simplify it. But yeah, that I will say is a standalone topic.
So basically it's just a primer for the next phases when we get into ML.
Yeah, it's a very, very like, yeah, primer is a good word. Yeah, it's a very like big picture thing of what are we actually doing here.
Okay, thank you.
You're welcome. So yeah, any other questions about topics or stuff? I was about to talk about like the structure of the next couple of weeks. All right, so where am I going? All right, so if we take a look at our calendar, and I hope we follow the calendar, tomorrow we'll be talking about A/B testing. It'll be our first Jupyter notebook that we've seen in a while. So that is already up on the study group repo for those of you who follow that. Thursday will be Bayesian statistics, as I just mentioned, very, very big picture stuff. I will be going through one very, very common interview question that combines conditional probability with the law of total probability and the Bayes theorem, which are things that I sort of alluded to at the start of this phase. And then topic 18 is going to be our intro to linear regression. I think it's a little bit weird that, you know, this phase is structured where, you know, you have 7 topics that's all stats and only like 3 topics that we have that's like actually what our project is about. But I will say there is some merit to that. The statistics stuff is kind of important to like really understand what we're doing in linear regression. I think I have written here that if you're done with statistics, feel free to skip to topic 18. I think it'll be very, very beneficial for you all to have gone through topic 18 when I talk about topic 18, just so you know if you have questions prepared, that'll just be, I think, better. So topic 18 happens on Friday. So that kind of gives, I think, the weekend and Monday or Monday for that to sink in. Topic 19, where we actually talk about more regression, multiple regression, is on Tuesday. And you can see I tend to go a little bit long on that study group, so I have it for 90 minutes, just because that one I really go into all the things that you need to know for your project. And then we do have that break day, which I mean, I think it also is worthwhile to have like some time for topic 19 to sink in. I don't know if anyone's looked at it, but topic 19 is also unfortunately very long, but also all important. And then topic 20, which is kind of like extensions to linear regression, but all stuff that are kind of optional for the project. So these are things that topic 20 are things that, if you, for some reason, got a really good head start on your project and just wanted to do a little bit more, you would do topic 20 stuff. And then I'll talk about the project on Friday. So I think having that little bit of space in between each topic just gives you time for all the new stuff to sink in. And then the project is going to be paired. Just to let you all know, the project is going to be paired. I'll be setting up pairs for the project next week. And prior to that, there is something that I wanted you all to start thinking about in your working groups, is that if you actually take a look at our phase 2, I'm going to give you all 2 options. And I'll definitely talk about this more at the end of the week. but there are two options of things for you guys to work on. First off, in the appendix, there is a full multiple linear regression project. So this actually like does a bit of like hand holding and walks you through the entire process of doing a project, which is almost identical to your end of phase project. So some students have found this helpful just because, you know, it's the same process that you'll be doing for your project. So one option for your working groups to do, and I'm actually gonna have just everyone in the working group work together because it is a lot of stuff to cover in like just under a week. So I'm gonna have like either 3 or 4 of you per group, just everyone work on it together. And I don't need you to submit every single lab. I think like if you could consolidate everything into like a notebook and like it doesn't have to be fully coded out, pseudocode can be fine, will be fine. And of course I'll like write out instructions for that and put it in Slack, so you don't have to remember this now. The other option, instead of doing this full appendix, is something a little bit shorter that you can actually start at the end of the week if you'd like. That there's this mini project here, regression modeling with the Ames housing data set. So within your working group, decide which one you want to do. This one I will say is more on topic 18 stuff, and then you can start hypothesizing and thinking about what you would do with topic 19 material. So I will say that I do want to see submissions from each working group by the end of next week on either this or the appendix project. I'm only saying this now because I know some of you have started working on topic 18 stuff. But yeah, I'm gonna write out instructions for this. But any questions on that? I know that was like a dump of new information. All right, well, if there are any other questions, I'm gonna write out instructions for this, put it on the homeroom, let y'all know in Slack that that is happening. Let's see. Yeah, I think that's all I have for you all. If there are any questions, feel free to let me know. And if not, I will see you all for one-on-ones or our study group tomorrow.
Ish, I have a question.
Yeah.
There are lots of information going around and I feel a little bit overwhelmed. For example, alpha, beta, power, sample sizes, p-value, effect size, everything. They are understandable, but I'm not too confident to if I can apply them to my work in, for example, in real projects. Do you have any recommendation or something about that?
Yeah, I think one reason why like a lot of these things I haven't really like, you know, emphasized that we need to know this is because a lot of these things we actually don't really need to know. In terms of resources, I did get a couple messages asking for more probability or statistic resources. I do think that like for data science purposes, the best resource out there, and I think most of y'all have said that you like those videos, are the StatQuest videos. I really do think if you're able to just understand what he's saying as he's explaining the concepts, it's good enough. A lot of these stats things are for data scientists, good to know, but we don't really need to use them in an application. I can actually like bring up a super quick example. I hope they have that here. For example, with like things like alpha, p-values, some of you might have seen this in yesterday's presentations, but something that's very common, whenever you run a linear regression, Python does it all for you. This library called stats models does it all for you and gives you this output. And I think a lot of us saw all of these outputs yesterday. And all you're gonna do is you're gonna take a look at these p-values and say like, all right, with a p-value of like 0.13, what does that mean? And of course, I'm gonna talk about in context, in a linear regression, what does this mean? Because it also depends on what the hypothesis is. But we're really just interpreting these. We never have to like do our own statistical test from scratch, which is why I feel like I haven't emphasized that, all right, you gotta know what alpha is, you gotta know what beta is, which I know like kind of sucks because it is still part of the curriculum and it is important to know. I will say that if you find yourself very, very interested in like statistics and especially a linear regression, that maybe as part of your interview prep, do look more into statistics. But most data scientists that come out of our program, we mainly focus on the modeling and predictive modeling aspect, which doesn't need as much statistical testing. All of these terms like, you know, power of a test, alpha, beta, what else, like test statistics, all of these are just good for us to know what these are, but we very, very rarely have to apply them. And when we do need to apply them, we can just really look them up. So I know it's not like a super good answer for like feeling better about the material, but fact of the matter is that for now, especially in this, like, we're doing stats in 2 weeks, we're doing like 2 semesters of statistics in 2 weeks. It's hard to, I don't think anyone can fully grasp the material in this amount of time. But I will put together, I do have more resources in terms of like books, like textbooks for statistics. So I'm happy to, I'll put them together in a list, hopefully, so for people who want to take a dive into that stuff after the program, that will be there for you. Hopefully that was a somewhat helpful answer.
Thank you, Ish.
You're welcome.
Kind of with what Ali said, it would be kind of nice to understand, and I think you kind of went into it a little bit, like an overview of how all these topics like kind of relate together.
Mm-hmm.
Like, I don't know, if like towards the end of the phase, just like reviewing like what we've learned, and I guess like the big picture, because when you're working on like each individual section, you understand the section, but I'm having trouble understanding how they like all connect together. And I know some of the topics are more standalone and are more for interview prep, but for the ones that are connected, it would be good to kind of understand like big picture of what this whole section is building to.
Yeah, absolutely. I think one thing that I'm going to send out that I already have is like a summary of all the statistical tests. So that I think will like put all of that together. The other part of the other, I guess, big category of what we were doing is the idea of like experimental design, statistical experimental design, which, and that part includes like, you know, your alpha, beta, power of the test. That, let me see if I can find like a good summary resource, and I'll like see if I can also like draw parallels to like where in our program that is. I'm pretty sure there are resources out there.
Yeah, that would be really helpful.
Yeah, let me write that down. Yeah, so the 2 main things, I don't think I ever talked about like big categories of what we were doing were like experimental design as well as statistical testing. But yeah, that's a really good request. So I'll do that. So yeah, I think one thing that will be super helpful is like when we talk about linear regression and this stuff, I think it'll also make things a lot clearer as to like what we really as data scientists, what parts of the things that we've talked about over the past week and a half we do need to know and what we don't need to know. But yeah, I'll definitely like put those resources together. If not by today, I'll get that by tomorrow. Awesome. Anything else?
Yeah, one thing. You mentioned some statistics videos that you said were really helpful for people, and I don't know if I missed that or if I forgot it, but could you put a link in the Slack or something?
Yeah. Let me see. I don't have that here, but yeah, I'll put a link in Slack. This guy, StatQuest, Josh Starmer from StatQuest, explains all these stats concepts really, really well. So I will send that out. Here we go. I have the link here, and I'm going to copy and paste it into your channel right now. There we go. Any last questions? Cool. Well, one thing that I have been recommending to people in my one-on-ones over the past half a week is that if you're feeling overwhelmed with statistics, I really, really recommend getting a head start on topic 18. One way of doing it is if you're doing topic 18 and you run into something that doesn't make sense, then go back and revise those particular sections. Another thing that came up today was that topic 18 is very, very long. 18 and 19 are both very, very long. And one method of doing those long topics have been helpful for some students in other cohorts is for those topics, because there's a lot of reading, but it's mainly like learning how to code these things out, is actually doing the labs first and then referring to the readings as you're doing the labs. Doesn't work for everybody, but worth a try if you feel like, the readings are getting too dry and boring. And I definitely relate to that as well. So just some things to try if you're finding that it's hard to get through some of the material. All right, I think there's nothing else. Going once, going twice. If there's nothing else, I will see you all at tomorrow's study group, and if not, at your one-on-ones. All right, bye everybody. Have a good rest of your day.
Thank you.
Thank you.
You're welcome.